x1 plus some element of the base field. X2 is mapped to a constant times x2 plus some polynomial in x1, and so on and so forth. So each generator is mapped to some constant times itself plus some polynomial in variables of lower indices. And once again, an example for n equals 3, you can send x to 2x plus 7. Here, this part in brackets is the, let's say, the part in lower indices. Y gets mapped to 2y plus x cubed plus 700, and z gets mapped to z plus 4xy squared plus y cubed plus 1. So many of you, I guess, have seen this before. And then we define the tame subgroup of aught AN to be the subgroup generated by these two subgroups, and we denote it by tame AN. And once we define these two subgroups, we can now distinguish between aught A3 and aught A2. So the first basic example is aught A1 looks like this. Every element of aught A1 is determined by the image of x, and x has to go to some ax plus b. A is a unit in your field, and b is any element of your field. Aught A2 is actually generated by those two subgroups that I mentioned before. And so aught A2 uh, is equal to tame A2. And one way of distinguishing it from aught A1 is by the fact that this is not it doesn't admit a structure of an algebraic group. So aught A1 you can write it as an algebraic group. Aught A2 you cannot. And one way of distinguishing aught A3 from aught A2 is by the fact that aught A3 actually is not equal to its tame subgroup. And this is a very famous result of Shestakov and Umirbayev from about, well, almost 25 years ago now. And Nagata's automorphism is shown to not be tame. And in that way, we can distinguish aught A3 from tame A3. So in this talk, we'll investigate these two questions. So are there other ways that we can distinguish aught A3 from aught A2? And are there ways to distinguish between aught A4 and aught A3? So perhaps unsurprisingly, we will say that the answer here is yes, we do have ways, and that will make up the content of this talk. Is that okay so far? Any questions? Okay. So structure and strategy. So as I mentioned before, the automorphism group of an affine variety is rarely an algebraic group, and aught A2 is one example of that. However, aught X does admit what's called an in-group structure, and basically this is a generalization of an algebraic group. We have a topology called the in-topology, and so with this topology, it makes sense to talk about open and closed sets and consequently about connectedness. And for the purpose of this talk, the only thing that you really need to remember is that these two objects, GA, which is the base field K with addition, and GM, which is given by the non-zero elements of K with multiplication, these are connected as both as algebraic groups and as int groups. And so how will we proceed going forward? Basically, since aught AN is so big, quote unquote, it can be hard to study it globally. And so what we try to understand, or what we try to do, is we try to describe its subgroups that are maximal with respect to some property. And this is somehow an analogy with what we do in many fields of mathematics. So when we study varieties, we often study divisors as, in a sense, maximal subvarieties. We study maximal ideals of rings. We study maximal chains of posets. And in the context of algebraic groups, we study maximal connected solvable subgroups. And so the analogy is with each of these examples. Okay. So let me just tell you what it means for a group to be solvable. Um, so a group is solvable if there's some natural number such that this sequence where you take commutator subgroups eventually reaches the identity. So here, this G1 is the commutator subgroup of G, G2 is the commutator subgroup of G1, et cetera, et cetera, et cetera. And so if that reaches the identity, your group G is solvable. And you can define the derived length of G to be the minimal I such that the ith derived subgroup is the identity. And basically, we're just preventing taking commutator subgroups of the identity over and over and over. So such a thing is called the derived length of G, and I will write it as dl of G. And now I have everything I need to define what it is for a subgroup to be Borel. So a subgroup B in odd X is Borel if it is maximal among connected solvable subgroups of odd X. And one of the nice things about Borel subgroups um, is that we will see later by a big theorem of four mathematicians that actually they admit a very nice structure. So before I go into that, I will just remind you about unipotent automorphisms and locally nilpotent derivations. So an automorphism is unipotent if it sits inside some copy of GA inside the automorphism group of X. And a derivation is locally nilpotent if for every element of your ring R, there is a natural number n such that if you apply your derivation enough times, you eventually get zero. And there is this correspondence between locally nilpotent derivations of a ring R and unipotent automorphisms uh, of the automorphism group of the corresponding affine variety. And these maps are given by the exponential map and its inverse, which is called the log. So here's a quick example of the exponential map in action. So here we have a polynomial ring in three variables. Then we define this exponential map from R to itself as follows. So you take an element R and you map it to the following element, which is also an element of your ring. And this map is an automorphism R, excuse me. And if you let U be the spec of that automorphism, you obtain a unipotent automorphism in the automorphism group of X. And this is generally, if you're given a derivation, you can generally calculate what this looks like relatively straightforwardly. So here we have a derivation, we apply it to X and then to 1. So we obtain dx equals 1, d squared x equals 0. We do the same thing by applying it to y and then to z. And then we run this formula here and we see where x gets mapped to, where y gets mapped to, where z gets mapped to. This is an automorphism of our ring, and the corresponding automorphism of the variety is the unipotent automorphism determined by D. Okay, so here is the theorem that I had mentioned before. And this is due to Cantat, Kraft, Regeta, and Van Santen. And it says that if G is connected and solvable, then you can write G as a semi-direct product of a torus and a group U, a unipotent group U, where U is the unipotent radical of G. So it's the set of unipotent automorphisms contained in G. And furthermore, U is nested. So being nested is a very strong property. And basically what it means is that you can write the set of unipotent automorphisms as an increasing union of algebraic groups. And this is much stronger than just being an ind group. Um, and so this is a very strong theorem, and as a consequence of this theorem, we can apply it to the very special case of Borel subgroups, because if we remember the definition, Borel subgroups are maximal among connected solvable subgroups of X. So in particular, they too are connected and solvable, and so we can apply this theorem. And just a bit of notation, so when B is a Borel subgroup, I will write B equal to T semi-direct product BU. And this BU is just saying that it's associated to B. Okay, so some basic examples. If X admits no GA actions, or equivalently, if the corresponding coordinate ring R admits no LNDs, then connected solvable subgroups are just tori. And that's because here this unipotent part is just trivial. So every Borel is just a torus, and since it's maximal in particular, it's a maximal torus. And so some examples of such things are one-dimensional varieties that are not isomorphic to A1, domains that have many units. So if you think about a local ring or a semi-local ring, and open affines of non-ruled varieties. Another straightforward example, any subgroup of odd X that's conjugate to a Borel subgroup is also a Borel subgroup, and that's not too hard to see. It's almost obvious. And finally, the example we discussed before, the Jonquière subgroup of odd AN, is another example of a Borel subgroup. Any questions about that so far? Okay, I'll continue. So some remarks. So again, X is spec R, and I've written my Borel subgroup B as a semi-direct product of a torus and its unipotent radical. So it's not hard to check items 1 and 2. So the derived length of a Borel subgroup is less than or equal to the derived length of its unipotent part plus 1. And this is basically because you have a short exact sequence here, and it's a general property of such guys that the derived length of the middle guy is less than or equal to the derived length, the sum of the derived lengths of the second and the fourth. And T is commutative, so it has derived length 1. And so you get this inequality. And the second inequality is essentially a bound on the number of, let's say, distinct commuting locally nilpotent derivations you can have of a variety. And you can get item 2 by considering the orbit of a general point of X, and using the fact that T acts faithfully to deduce that the dimension of T is less than or equal to the dimension of your variety. And now that we have these upper bounds on the dimension of the torus and the derived length of the Borel subgroup, we can try to classify Borel subgroups by their derived length and by the dimension of the torus that appears. And since we know that a conjugate of a Borel is Borel, and also it's easy to check that by conjugating you preserve these values of derived length and dimension, we actually the real question is what we actually want to do is we want to classify these Borel subgroups up to conjugacy. And there are some results about this that are known. It's a classical result about algebraic groups that all Borel subgroups of an algebraic group are conjugate. And in the special case of aught A2, we still get that all Borel subgroups of ought A2 are conjugate. And this is a result of Beresh, Eshmetov, and Eshmetov from about 10 years ago. And it sort of motivates the next question is, well, what can we say about Borel subgroups of ought X for other X, in particular when X is affine space? So we will see that this type of analogy is very far from being true, and we will show that you actually have tons and tons and tons of non-conjugate Borel subgroups of ought A3. Okay. Um, so now I want to introduce something called de Jonquière-like Lie algebras, and these were introduced by Perepechko in a very nice paper where he constructs this correspondence or proves this correspondence between maximal nested unipotent subgroups and maximal de Jonquière-like Lie algebras. So basically, you start with a family of commuting, pairwise commuting, uh, locally nilpotent derivations of your ring. And then you define these subrings, AI, to be the intersection of all of the kernels whose indices are greater than or equal to I. So the AK is just the kernel of the last one. AK minus 1 is the intersection of the kernels of the last two derivations, all the way down to A1, and that's the intersection of all of the kernels of the derivations that appear. And then you define two Lie algebras, Lie subalgebras of the Lie algebra of derivations of R in the following way. So you define this straight L of d1 to dk to be this direct sum. So you take the intersection of all the kernels, you multiply it by d1. You take the direct sum with the intersection of all but one of the kernels, you multiply it by d2. The direct sum with et cetera, up to the kernel multiplied with the last derivation. And then you can check that this Lie subalgebra is actually contained in the set of locally nilpotent derivations of R. And then you look at this curly L, which is a bigger Lie subalgebra. And it's a similar object, except for the fact that you are allowed to localize at the non-zero elements of A1. So if something is, so you look at A1, you localize at all the non-zero elements, and you get a subset of the set of locally nilpotent derivations of S inverse R. And then you take anybody that lives both in there and in the set of derivations of your original guy. And again, you check that this is actually a Lie algebra and it's also contained in the set of locally nilpotent derivations of R. And it's easy to see that this curly L contains this straight L, and Lie subalgebras of this form are called de Jonquière-like Lie subalgebras. So, I mean, this is maybe a bit
Michael?
symbolic, but you can get a bit of intuition for what this looks like, what these objects are by doing an example. So here I'll share an example also from,
Michael,
yeah,
this is Daniel.
yeah.
You forgot one condition in the definition of yes. To, the
Yeah,
definition.
this
Here.
condition on D1 decay. Yeah.
Yeah, yeah. So D1 DK have to be linearly independent over the ring R.
Ah, okay.
Mhm.
Yeah, so okay, thank you.
That's an
So
assumption. Yeah.
yeah, thank you. Otherwise, okay, thank you for that comment. So if you don't assume linear independence, basically your AKs and your AK minus ones, etc., can essentially all be the same thing. and you want to avoid that problem. So you want this to be basically a sequence of subrings of decreasing transcendence degree. Thank you. Thank you. Okay, so I just I left the definitions here, and here is an example of Perepechko. So we consider the pair d1, d2 to be these two derivations, and it's fairly straightforward to check that the kernel, well, it's obvious that the kernel of the last guy is a polynomial ring in X and Y. And then you can check that the intersection of the two kernels is a polynomial ring in X. And this Lie algebra L of d1, d2 is, well, kx. This is your a1 times the first derivation plus kxy times the second derivation. And this curly L, where we're allowed to localize at the non-zero elements of kx, gives you this Lie algebra. So it's well, any element of the function field of kx times your first derivation plus I guess a polynomial ring in one variable over the function field times your second derivation. Anything in there that is remains a derivation of R. And you can check that actually the partial derivative with respect to y is in this curly L d1, d2, but it's not in your original straight L d1, d2. So here we have a proper inclusion. However, if if we are clever about our choice of derivations, we can somehow replace this d1, d2 by some other derivations e1, e2, so that this curly L is actually can be written in the form of a straight L. Um, so in some sense, in this special case, the Lie algebras of this form, this curly L, are not necessarily bigger, quote unquote, than the Lie algebras of this form, this straight L. So this motivates a natural question. Um, I guess okay. So the natural question is, can you always replicate this process? Can you always change the derivations here, D1 and D2, so that you can replace this localization tech trick that we need to usually take by other derivations where it's not required anymore, where you don't actually have to localize at the intersection of the kernels? And actually, the answer is no. Sometimes you have no choice but to preserve this localization at S inverse. And here is an example of such a thing. So if you consider this pair of derivations, d1 to be a partial derivative with respect to y, and d2 to be u d by dz minus v d by dy, then you can never write this Lie algebra curly L of d1, d2 as a regular L of e1, e2. And so somehow this is telling you that Lie algebras of these two forms are different from one another. And the same actually goes through, or for any n greater than equal to 4, you just need to consider certain extensions of these derivations to larger dimensional polynomial rings. So this is the question that I just mentioned before. So if you have some Lie algebra that looks like this, L curly L d1 up to dk, can you always find a tuple e1 to ek such that this regular L is equal to curly L? And our proposition says that if you have a three-dimensional UFD, you can always do such a thing. And If that's not the case, so if you have a three-dimensional non-UFD, you can't always do it. And if you have a polynomial ring for n greater than or equal to 4, uh, you can't do it. Um, so just some remarks about that proposition. So if you're looking at the special case of Lie algebras where k equals 1, so curly L of just a single derivation, or k equal to the dimension of R, so as many derivations as you can possibly have, then yes, you can write your curly L as your Lie algebra curly L as a straight L. And in the three-dimensional case, because of the first remark, really the only interesting case is the case where you have two derivations in your de Jonquière-like algebra. And um, the fact that this is true depends heavily on the fact that the dimension of the intersection of the two kernels is 1. And so somehow this is just a, a very big restriction that says that you can always do exactly what we did in Perepetchko's previous example. And so what is this saying group theoretically? Basically, what it's saying is that for n greater than 4, if you look at the unipotent radical of your Borel subgroup, it need not look like a semi-direct product of this form. So when you're working with three-dimensional UFDs, the unipotent radical is essentially always written as a semi-direct product of exponentials of intersections of kernels times a derivation. But that's not true anymore in higher dimensions. So this is one feature that distinguishes between Borel subgroups of odd A4 and Borel subgroups of odd A3. Somehow the automorphism group of A4 is more complicated than that of odd A3. Okay, so one of our results tells us that actually there are bijections between the following sets of objects. Um, the set of Borel subgroups of odd X, the set of maximal nested unipotent subgroups of odd X. So that's our part. And then this correspondence between the maximal nested unipotent subgroups of odd X and maximal Lie subalgebras of the form that I mentioned before. This is a nice result of Perepetchko. And then our previous proposition tells us that for three-dimensional UFDs, we also have a bijection with maximal Lie subalgebras of form straight L D1 to dk. So let me just give some remarks about the first equivalence. So first, if you have a Borel subgroup T semi-direct U, you show that the unipotent radical is maximal among nested unipotent subgroups. And after you do that, if you are given a maximal nested unipotent subgroup, you can always choose a Borel that contains it because it's maximal amongst all connected solvable subgroups. And so since the unipotent radical consists of all unipotent elements, in particular, it contains U, and by the maximality of U, you know that those two groups are equal. So the unipotent radical of the Borel you chose has to be equal to the maximal nested unipotent subgroup that you started with. And so that shows that for every maximal nested unipotent subgroup, you can find a Borel subgroup whose unipotent radical is that thing. And then you need to show that it's unique. And to show that it's unique, you assume that you have two tori that are maximal amongst tori that normalize U, and you show that if you have two such tori, then actually those two groups that you construct are actually equal. So that's a bit of that. Those are the ideas behind the equivalence of 1 and 2. And then, as I mentioned before, the equivalence between 2 and 3 is one of the results in Perepechko's paper, and the equivalence of 3 and 4 is the previous proposition that I mentioned. So let me just tell you quickly what the maps from the theorem are. So if you have a de Jonquière-like subgroup, uh, the exponential map is what gives you your nested unipotent subgroup. It's the exponential map that I gave you before. And to go in the other direction, if you start with a unipotent subgroup, you can define so for each unipotent automorphism, you can define this guy log u, which gives you a derivation of R. And if you apply this map log to the entire set, you get this Lie subalgebra curly L. And to go from maximal nested unipotent subgroups to Borel's, basically you choose any maximal torus, any torus that's maximal among those normalizing U. And to go from Borel's back to nested unipotents, you just take the unipotent radical. So those are the maps that take you from one object to another. So a remark. Basically, what the next few slides discuss the relationship between the derived length of B and the derived length of the unipotent radical. And we saw before that the derived length of B is less than or equal to the derived length of the unipotent radical plus 1. Now, if you have no torus in your Borel, then it's obvious that B is equal to BU, and clearly the derived length of B equals the derived length of BU, just because the two things are equal. Now, what happens if you have a torus? Is it the case that the derived length of the unipotent radical is strictly less than the derived length of the Borel itself? So for algebraic groups, it's not necessarily the case, and here is one such example where the derived length of G is not equal to the derived length. Sorry, G is not equal to GU, but the two derived lengths are equal. So the question now is, okay, can this happen? Can this happen in the setting of automorphism groups? And in fact, it can happen. And so if you let R be a two-dimensional finitely generated domain with the following properties, so you choose R that's not rigid, that has trivial units, and does not admit a non-trivial Z grading. And if you consider the cylinder over R, then you can cook up a Borel subgroup of aught X with the property that B is not equal to its unipotent radical, and the two derived lengths are equal. Now, luckily for us, or let's say interestingly, when you look at the special case that X is affine 3 space, actually you always get that the derived length of the unipotent part is strictly less than the derived length of the Borel itself, as long as your torus is non-trivial. So the lemma is as follows: if B is Borel in aught A3 and T is non-trivial, then the derived length of the unipotent part is actually equal to the derived length of the Borel minus 1. And the proof is basically a case-by-case verification. You look at each of the various possible derived lengths of Borels, and you take advantage of properties of LNDs of the polynomial ring in 3 variables. And so what this lemma tells us is that the derived length of B is actually entirely determined by the derived length of the unipotent radical and the dimension of T. So the next thing I want to discuss is basically what do conjugacy classes of Borel's look like for the various derived lengths of BU, and dimensions of T. And I will explain what I mean by many later, but I just want to give some first. I just want to give some remarks about this table. So first, the first row of the table is essentially due to the fact that um, homogenization of locally nilpotent derivations uh, exists and gives you a locally nilpotent derivation. And the point here is that um, if you have a torus and your variety is non-rigid, then you will never have a Borel subgroup that consists only of a torus. You can always find uh, a bigger connected solvable subgroup that consists of the torus multiplied by some unipotent part, yeah, some unipotent guy. Um, and so that explains why your first row is 0. There are no conjugacy classes of Borels with that consist only of a torus. The last row and the last column are based on what are now well-known facts that if you have a torus whose dimension is equal to the dimension of your variety, then it's conjugate to Jonc. Or if you have uh, if the unipotent part of your Borel subgroup has derived length n, which is also equal to the dimension of your variety, then again your Borel is conjugate to Jonc. And so um, in each of these cases, basically you have the only possibility where the dimension of your torus is 3 or the derived length of your unipotent part is 3 is is that your Borel subgroup in fact is conjugate to Jonc. So that explains this one over here in the bottom right corner and the zeros on the last column and the zeros in the last row. And so the interesting part really is what is happening on the, let's say, the inside of the table. So the second and third rows and the first three columns. Um, and so I will go into what's happening for this red part of the table, and the rest of the story is essentially done in a similar way, although using different, slightly different tricks, but variations on the same theme. Okay, so first, if two Borel subgroups are conjugate, then their corresponding Lie algebras are conjugate. And so the example we'll focus on for the next few slides is the special case where the derived length of BU is 1 and the dimension of the torus is 0. So this is really the special case of commutative Borel subgroups. And so a proposition, so assume B is a commutative Borel subgroup, then the Lie algebra is just this curly L of some D by Perepechko. This is equal to some straight L of some D by the proposition that I mentioned before. And this, by definition, is just the kernel of D times D. Now, this D must be irreducible, non-commuting, and non-homogenizable. So what do I mean by non-commuting and non-homogenizable? Well, I say that a derivation D is non-commuting if whenever it commutes with something, those two guys have the same kernel. Um, and I say that it's non-homogenizable if it's not homogeneous for any non-trivial Z grading G. So where are these conditions coming from? So the fact that it's irreducible comes from that our D must be irreducible comes from the fact that this LD is maximal. If D were not irreducible, you can hook up a bigger Lie algebra by including the irreducible guy with the same kernel. D needs to be non-commuting because the derived length of BU is 1. And if D commuted with some guy with a different kernel, then you'd be able to cook up you would have a unipotent subgroup of derived length too. And just a remark, it's well known that an irreducible LND of KXYZ is non-commuting if and only if its rank is 3. And the fact that D is non-homogenizable comes from the fact that the dimension of T is 0. So basically you can't have a torus that normalizes the exponential of your derivation. Otherwise, you'd be able to build um, a bigger connected solvable subgroup. So those are where these conditions come from. Now, it's not so hard to check if a derivation is irreducible. It's not so hard to check if a derivation is non-commuting. Um, how do you check that a derivation is not homogenizable? Uh, so in this case, we were able to construct homogenizable derivations of rank 3 using the following 3 things. So we use the fact that C star actions on C3 are linearizable, and this is a big result of Korus, Russell, Kaliman, and Makar Limanov, I think. I think. And in algebraic terms, this is saying that every Z grading of a polynomial ring in 3 variables admits a homogeneous coordinate system. Then we use a result that's specific to homogeneous LNDs of rank 3. And it turns out that if you have a homogeneous LND of rank 3, then when you take the intersection of the kernel with the degree 0 subring, you always just get the base field. And if you combine these, well, you use the first item to prove the second item. And if you combine the second and the third items, the fact that the plinth ideal of every LND of K3 is principal, you can actually show that you can actually construct families of LNDs that are not homogeneous with respect to any Z grading. So you don't need to worry about the details here, but basically the main idea here is that you choose some D, any integer, and you pick a point in affine space of dimension D minus 3. And for each point, each such point A, you cook up a derivation delta A, this delta A at the bottom right. And all of these points give you distinct derivations delta A. And for each of these delta A's, they are all irreducible, locally nilpotent. They all have rank 3. And they are not homogeneous for any non-trivial Z grading of B. And so item A is relatively straightforward to prove. You can just apply your delta A to X, Y, and Z. Item B, you can check. I mean, it's not immediately obvious, but you can see that these are very, very similar to Freudenberg's derivations that he discovered about 30 years ago that have rank 3. And so it's not hard to, I guess, convince yourself that these have rank 3. Item C is basically an application of the previous slide where you use these properties of homogeneous LNDs of rank 3 to show that delta A can't be homogeneous. And then you can argue that if A and B are different, then delta A and delta B are non-conjugate. And here you use properties of the plinth ideal. Again, you use the fact that it's principal and the fact that any automorphism must map one plinth ideal to another. And what this gives you is the following. So for each distinct A and B in affine space, if you take the exponential of the kernel of that derivation times the derivation, um, for distinct A and B, those guys are non-conjugate commutative Borel subgroups. And each of these derivations are, let's say, quote unquote, parameterized by affine space. So you have a family, you have a family of derivations that can be parameterized by a variety of arbitrarily large dimension, such that for each point, you can associate a Borel subgroup and distinct points give you non-conjugate Borel subgroups. So basically, the way I write that is that you can basically parameterize the conjugacy classes of Borel subgroups of derived length 1, such that the unipotent part has derived length 1, uh, and the torus is zero dimensional by quote unquote A infinity. And the same idea goes through for each of these four items here, wherever you see A infinity. And there's one special case where you get countably many Borel conjugacy classes of Borel subgroups. And this is really because the fact that you have a two-dimensional torus puts a big restriction on what can happen. So that's the story about conjugacy classes of Borel subgroups of Aut A3. And now we can sort of just fill in the answers to the questions that we mentioned at the beginning. So in particular, how else can we distinguish Aut A3 from Aut A2? So if we remember the theorem of Beresht, Eshmetov, and Eshmetov, all Borel subgroups of Aut A2 are conjugate to Jank, but for Aut A3, that's not the case. We have commutative Borel subgroups. We have four quote unquote infinite dimensional families of non-conjugate Borel subgroups, and we have one family of countably many non-conjugate Borel subgroups. And again, our study of Borel subgroups allows us to distinguish between Aut A4 and Aut A3. So if B is a Borel subgroup of Aut A3, then the Lie algebra of the unipotent part always has this very special form. But this is not the case for Borels of Aut AN when n is at least 4. And so these, I guess, are, let's say, partial answers to these two questions. And we can ask similar questions, or we can push this a little bit further by asking the following. So are there commutative Borel subgroups of Aut A4? At the moment, we don't know the answer to that question. In fact, we don't even know the answer to the simpler question, does there exist a non-commuting element of LNDK4? So far we've only, whenever we have a locally nilpotent derivation of K4 that we know of, we can always find another guy with a different kernel that commutes with it. So we couldn't find such a guy yet, although somehow it seems like such a guy should exist. And at the moment, we don't have a good way of distinguishing between Aut A4 and Aut A5. So it would be nice to come up with some way of doing that. I think that's everything I wanted to say. So thank you very much.
Thank you, Michael. Are there any question?
Maybe I'll ask a question.
Sure.
May I ask you about, in dimension 3, on A3, you don't need to localize
Sure.
your result, right?
Yeah, I guess you're talking about the proposition that I mentioned where you can always replace your D1 and
Preferred
D2
L.
here.
Yes, by another. Yes. Did you check this, for example, with for the bus example with Natat automation? That is it's generated by bus example and by D or DZ. This and I didn't check actually that you can find this E1, E2, but by proposition you can. It is interesting to find them.
Yeah, so
Yes.
I expect we can do it. I think we could probably follow the proof of the proposition. I expect it should be able to cook up the E1 and E2.
Is it more constructive?
I'm
Or
sorry?
is the proof constructive? Does it give E1, E2?
I don't think it's constructive explicitly, but I mean you can get I mean we know what the recipe looks like more or less. I think we use
Okay.
we use the fact that we use the fact that this intersection of kernels will be a PID. So I mean
Mm.
I expect that we would be able to do it. I expect that we would be
Okay.
able to do it.
Thank you.
Sure.
Maybe one more question. Do you hear me?
Yes.
If it's possible to return to this table with a result,
The,
I have today non-stable internet connection, so maybe I didn't understand. Like which we saw just a moment ago. Okay, what is the difference between between red and black A?
the red is the example that I focused on when I went through the details. There's no difference.
So this is all not conjectural. This is proof that you also have when you have black A. This is also a result. This is known to be
Yes,
infinite.
we have families for each of these four cases, and the red is just the examples that I went through today.
This Z times Z means that you have countably many conjugacy classes, right?
Correct, correct. Actually, I might be mistaken. Okay, so it's countably many for sure, but maybe I should have written n times n because I think, I mean, it doesn't change anything for the cardinality, but I think it's basically parameterized by naturally by I and j natural numbers. So maybe z times z is the wrong thing to write, but it's still true. Yeah,
Okay, thank you.
sure.
So in other cases, you have just the modular space of Borel of this type is exactly the affine space of infinite dimension.
Okay,
So that really
so
your uh, okay.
so maybe so actually maybe I'm not being precise enough. So I should say at least. I should say at
Ah,
least.
okay, okay, okay,
Sorry, maybe
okay.
I
It
don't know that we
contains.
have all of them. I don't know that we have all of them. I know that you can cook up at least this many by the construction that I mentioned before.
Okay, okay.
Sorry.
Thank
So
you. Thank you.
Further question?
Maybe I'd like to ask about examples with based on two derivations. So is it are they similar to the non-commuting case that you presented?
sorry, are you
So
you're asking about the other three cases?
yeah, I'm asking about the case, for example, below red,
Yeah.
the case 2, 0. Is it
Yeah,
much different when you
so
take two derivations?
the 2-0 case. Yeah, the 2-0 case. So I think we took a pair of commuting non-triangularizable derivations, I think, or one of which was non-triangularizable. Um, and then we did sort of the same trick as uh, here to cook up a commuting pair that are non-homogenizable. So
I
yeah, the style of argument is the same, but rather than using these properties of rank 3 LNDs, you do something similar. Basically, if you yeah, the argument is similar. You again use the fact that the plinth ideal is principal, but and I think you again use the fact you use 1 and 3, but you apply it to a commuting pair of quote unquote ugly enough rank 2 derivations. It's a
okay.
bit it's not a great example. I can send you the examples, no problem, and you can have a look. But yeah, it uses 1 and 3
uh,
and not 2.
okay. Thank you a lot.
Sure.
Question? That's your last chance. Okay, if not, we thank Michael again. And this is it for today. Next seminar will be on October. We have our summer break. I think Ivan, Andriy, Alvaro, and I will keep you posted about what will happen next October and the months after.
Yes.
Okay,
Okay.
so
Thanks,
goodbye,
Michael.
goodbye, everybody.
So,
Thanks, Michael, and have a good summer.
Thanks for coming,
Thanks.
everybody.
thanks, Michael,
Ciao.
for very, very, very nice talk. Thanks.
Thanks.